My name is Duncan, and I will be talking to you today about my work with hybrid simulation and seismic testing of environmentally damaged bridge columns. I'd like to take a second to acknowledge my research advisor, Professor Claudia Ostertag, as well as Salim Gunai and my colleague Ian Williams. So this story that I'm going to tell you today starts with the state of American highway bridges. And as many of you may know, they are in disrepair. Of the over 600,000 highway bridges in the United States, more than 67% are made of reinforced concrete or pre-stressed concrete, and almost 10% of these highway bridges in the United States are structurally deficient, meaning that they require significant repair or replacement. And the ASCE estimates that there is about $120 billion in backlogged repairs and replacements that have yet to be undertaken. When we compare these facts with the USGS seismic hazard map of the United States, we can see that 34.7% of deficient reinforced concrete bridges are in states with high seismic hazard, and close to 80% of those bridges are in states with moderate to high seismic hazard. Given that building codes don't account for deterioration of buildings and bridges directly, it's surprising that such little research exists on structural performance of deteriorated bridges. So specifically, I'm looking into corrosion in highway bridges, and corrosion is a leading cause of damage to bridge structures, specifically in reinforced concrete bridges. And the National Association of Corrosion Engineers estimates that around $17 billion is spent annually on corrosion-related repair and replacement in reinforced concrete bridges alone. And if you look at indirect costs, which are much harder to quantify, the Federal Highway Administration acknowledges that costs such as traffic delays could be 10 times as high. So I know this isn't a corrosion conference, so I'll try and get into the hybrid simulation aspects, but briefly I just want to touch on a little background. And the corrosion process in reinforced concrete can be broken down into two stages. You have an initiation period where the reinforcing steel is passive due to the high pH of concrete. And during this period, aggressive agents like carbon dioxide from the atmosphere or chlorides from seawater or de-icing salts are penetrating into the concrete cover and will eventually depassivate the reinforcing steel, which would take us into the propagation stage, during which rebar is actively corroding until you have cracking in the concrete, at which point the damage is accumulating at an accelerated rate. You eventually reach spalling of the cover, and then at some point you reach some acceptable limit where the structure either has to be repaired or replaced. And just to give you some examples of damage, so here we see some significant spalling, and as well as another, even before you reach spalling, you can have damage that affects mechanical behavior, especially splitting cracks, which deteriorate the bond between reinforcement and the concrete, and this significantly deteriorates flexural behavior. This is significant because this type of damage can often be found in the plastic hinge region of reinforced concrete bridges, and given how important these regions are to drift of bridge structures, it's important to understand the interactions between corrosion damage and seismic performance. So there are a lot of challenges when addressing this problem. First of which is that concrete damage due to corrosion is difficult to model, and it's difficult to incorporate this into a structural model. Additionally, corrosion damage occurs slowly, which adds to the difficulties with large-scale testing, it being on its own difficult and cumbersome, even without considering complications of corrosion. So that brings us to a unique solution of hybrid simulation, where we can scale down from full-scale testing and focus on just an isolated component. And so in this experiment, we're considering accelerated corrosion on a physically manageable substructure, specifically just the plastic hinge region of a bridge structure. And then we can, after inducing corrosion on a specimen, we can use hybrid simulation to determine the influence of damage in this region on the overall performance of the bridge. So the bridge of interest that we're considering is a single column California bridge structure. And we see that we have an analytical substructure, and we've replaced the plastic hinge with an experimental substructure. And so this is just a concrete column section, and it has been separately corroded and with splitting cracks induced, similar to those that we saw in the image I showed before. And if we replace this portion of our open seas model of the bridge structure with this pre-damaged substructure, we can capture the complexities of damage and incorporate those into our open seas model without having to explicitly model them. So the way we are doing that is we have a 3 actuator setup, and 2 actuators are used axially, and those are applying both the axial load as well as rotation to apply moment. And we have a lateral load to apply shear and also moment to the substructure. And a closer look at our test specimen. So we have scaled down with a linear scale factor of around 8, so 8.37, and we've taken a prototype column, and so we've scaled it down to be more physically manageable. And so we have a 26-inch section with reinforcing ratios shown here, and we've casted some high-performance concrete end caps to make sure that our boundaries remain elastic and don't contribute to damage that we're seeing when we're conducting the test. So to look closely at the environmental conditioning, this is how we are applying corrosion damage to this specimen. We're immersing it in a saltwater bath, and then using a potentiostat to apply a constant current. And while we're doing that, we're measuring the potential, which you can see fluctuates here with the formation of cracking in the specimen. And just to reiterate the importance of these splitting cracks, so this is the behavior that we are trying to characterize with this study. Splitting crack damage has been shown to significantly reduce the flexural capacity of elements. And so we want to see in a bridge structure what is the overall performance, and how does this influence when this damage occurs in the plastic hinge region. So we are testing this in Davis Hall, and we're aiming to test this week, so we're testing actually on Thursday. But to give you a flavor of what the test setup looks like, again, you see our actuators in the vertical direction as well as lateral, and our substructure, which is here shown. And so more background and future work that can be done with this. In addition to determining the behavior of existing structures, we also see this as a great opportunity to use hybrid simulation to investigate different systems and specifically different materials and how they would perform in a similar situation. My research group focuses on construction materials, and so we like to implement novel materials as a solution to issues such as deterioration due to corrosion damage. So we will be utilizing hybrid fiber reinforced concrete and hybrid fiber reinforced concrete utilizes multiple scales of discontinuous fibers in order to increase the ductility and toughness of concrete. So as you can see in this case, the fiber combination that we utilize allows us to achieve diffuse microcracking, and that allows the material to achieve strain hardening and deflection hardening behavior, which has been shown in bridge columns to increase the toughness of structures. So in the first test here, this is a conventional concrete column by Vesna and Boja at UC-Berkeley, and that can be compared with this test by Marios as well as other collaborators. And the high FRC column had significantly improved performance up to a 50% higher drift, and they were similar columns and plan, with the main difference being the type of material used, specifically hybrid fiber reinforced concrete versus conventional concrete. So additionally, in addition to the seismic behavior of this material, it has also separately been shown to improve the corrosion behavior, both in the initiation period as well as the propagation period. And this comes down to crack control. So we tested fiber reinforced concrete beams compared with a control specimen, and due to this diffuse microcracking under a given loading, we were able to decrease cracking in the specimens, which maintains the concrete cover and prevents chloride diffusion under an extended period of saltwater ponding. So these specimens were, after preloading, were ponded with saltwater for 2 years, and you can see the behavior. The hybrid fiber reinforced concrete beams eventually depassivated and entered the propagation phase, but no significant damage occurred over the 2-year period. Meanwhile, in the control specimens, they completely split open due to splitting cracks from corrosion. Their initial cracks were transverse and some splitting from the flexural tests, but this damage, for example, the column being split in half, was done due to corrosion damage. And if we look at the flexural behavior of these elements before or after corrosion, the top specimens are our hybrid fiber reinforced concrete specimens, with the black line showing the behavior prior to corrosion. So these were sacrificial specimens, obviously. And when compared with elements after 2 years of corrosion damage, they achieved very similar behavior. Whereas with the conventional concrete specimens, the preloaded specimens, which you see here, were too damaged to test after the 2-year period, so they essentially had no residual stiffness left. Meanwhile, the control specimens, so they were unpreloaded, could be tested after the 2 years, but even in those you see a significant decrease in strength. And so this shows that, or I wanted to touch on that, under the same service loading, hybrid fiber reinforced concrete can be used to extend the service life of concrete structures. And so the goal here is to apply this to bridge elements, and specifically in this case we're considering the plastic hinge. And the reason hybrid simulation is significant and important to this test is that it really is the only feasible way to incorporate this durability component with seismic testing. Again, due to the fact that fully analytical simulations cannot be done accurately, and that corroding a full-scale specimen and then performing a seismic test is expensive and impractical. So hybrid simulation provides a low-cost alternative and can maintain accuracy even with complex damage conditions. And it provides us with a repeatable test procedure to explore new materials for use in bridge columns.
Thank you.